One of the most important topics in all of chemistry is the idea of chemical equilibrium. And chemical equilibrium is just a description of the fact that reactions can both go in their forward direction, as we've been thinking about them, but they can also reverse. Any chemical reaction that we can turn around and write it in the opposite direction, right? So carbonic acid, H2CO3 gas can decompose to form carbon dioxide molecules and water molecules, or turn that around, carbon dioxide can interact with water to form H2CO3 molecules. When we think about that, I mean, we can do it on paper, but really a lot of reactions physically do that. And in fact, all reactions to some extent can react in both directions. So we can express this behavior by writing, instead of two different reactions, by writing one reaction with that two-ended arrow, and describe this as being at equilibrium. Now, we've already talked about equilibrium. We didn't use the word equilibrium. I might have used the word equilibrium, but think back to that vapor pressure colligative property that we talked about. In a sealed container, I've got some liquid, and if I leave it just sit, eventually we'll get to a point where we've got a vapor pressure up here. And what do we say? We said that the rate of particles leaving the liquid phase into the gas phase is equal to the rate of particles going from the gas phase back to the liquid phase. That doesn't mean that it's the same particles that are up here in the gas, but it means that on average over time, there are the same number of particles up here. That is equilibrium. The reaction of going from liquid to gas is equal, the rate of that reaction is equal to the rate of going from gas to liquid. So a few things. First of all, equilibrium is a dynamic process. And this is one that trips people up sometimes. What do we mean by dynamic process? We mean that the forward reaction and the reverse reaction are always happening. It's just that when we're at equilibrium, the rate forward and the rate reverse are the same. So to a macroscopic outside observer, it doesn't look like things are changing. Once we get to equilibrium, it's also important that we know that the concentration of reactants and the concentration of products are constant. They don't change. That doesn't mean they're equal, but it means they don't change anymore. So again, the rates are still happening. The reactions are still happening back and forth, but they've balanced each other out so that now the concentration of reactants and the concentration of products no longer changes. We can use that to put together something we call an equilibrium constant. So KEQ, the equilibrium constant, is equal to the concentration of products raised to some power divided by the concentration of reactants raised to some power. And if we think about that, what does that mean? If KEQ is greater than 1, if KEQ is greater than 1, that means that the numerator, the top number, the products, is a bigger number than the bottom number, the reactants. So we call that a product-favored equilibrium. If KEQ is less than 1, well, now it's just the opposite case, right? The bottom number is bigger than the top number. There are more reactants than products. We call that a reactant-favored equilibrium. So let's take a look at a problem. We'll use a generic equation for this problem. You're studying the reaction 2A plus B gives me C plus D. When the reaction reaches equilibrium, you find the following concentrations. There are all those numbers, I don't need to read them. What's the value of the equilibrium constant? So our generic form of an equilibrium constant, KEQ, is equal to products raised to some power, and the power is the coefficient in the balanced equilibrium reaction. So C raised to the first power times D raised to the first power divided by the reactants. A raised to the second power, B raised to the first power. Plug in all of our numbers and we get 9.07 for the equilibrium constant. 9 is greater than 1, so this is a product-favored equilibrium under this set of conditions. Now, one important little note here. I've done a lot of nagging for you to always include units on things. And then we get to equilibrium constant, and it turns out that equilibrium constants don't have units. There is a real mathematical reason for this. It's beyond what we really need to go through in this course. But here you get a break. You can leave the units off because, formally speaking, equilibrium constants do not have units. So we can avoid them. We can ignore them going forward. So there's an equilibrium problem. Now, one of the things we can do with equilibrium and the equilibrium constant is we can use this to assess whether a reaction is at equilibrium or not. And we're going to do that using something called a reaction quotient. So a reaction quotient, mathematically, a reaction quotient looks exactly like an equilibrium constant, but now we don't know if we're at equilibrium. So I'm not going to have those little EQ tags on all of my concentrations here. If the value of Q is equal to the value of K, if the reaction quotient is equal to the equilibrium constant, well then our reaction is at equilibrium. Handy little reference point. But we can also assess what direction it has to go. We can also assess where it is with respect to equilibrium. So if the value of Q is larger than the value of K, then what does that mean? If it's too big, that means the numerator is too big. The numerator is products. So there are too many products, and the reaction has to shift to the left towards reactants to get to equilibrium. Likewise, if the value of Q is smaller than the value of K, then my denominator is too big. I have too much reactants, and the equilibrium has to shift, or the reaction has to shift two products towards the right to get to equilibrium. Again, let's just take a look at an example here, and it'll make a little bit more sense in context. So we're studying the same reaction. 2A plus B gives us C plus D, and we found that under some set of conditions that we're working with now, the value of K is 0.537. So we mix things together and we let the reaction start to occur, and at some point we find these concentrations of everything. Is the reaction at equilibrium? So we can plug these concentrations into that form of the equilibrium constant that we call the reaction quotient, calculate it out, and we find that the value of Q here is 7.82. 7.82 is not equal to 0.537, so it's not at equilibrium. Formally, I've answered the question, right? It's just asking yes or no, is the reaction at equilibrium? And no, it's not, because these two numbers are not equal. But we could also look at this and say, well, Q is too big, so to get to 0.537, it has to shift towards the reactants, towards the left, to get to equilibrium in that case. So reaction quotient, really just a way to use the mathematical form of the equilibrium constant to assess where a reaction is. We're not going to spend a lot of time on equilibrium, but it's going to come up over and over again in some of the other things we talk about. So it's important that we've got that concept down. We'll look at it a little bit more, and I'll see you next time.